In this video, we'll go over the moment of inertia idea again, along with the angular momentum principle. We will apply this to two different problems, one of which involving a merry-go-round and the other one with a string unraveling on a disc. Now remember, in society here we have a lot of different examples of this sort of stuff happening. We have a propeller, anytime you open a door, angular motion of a ballerina, you're picking up something off the floor. We got gear ratios, excavators, cars, wrenches, pulleys, and so on. And we will apply some of these ideas to these problems, and hopefully when we do that we'll learn more about the angular motion in the world around us. And so what we'll do here is we'll look at the moment of inertia and center of mass idea again. Remember, when you have a center of mass, you can take the weighted average and try to figure out where the center of those masses are, and then the resistance to angular motion changes based on how the mass is distributed about an axis of rotation. And so you have different shapes rotating about a particular axis, and that you can basically solve for a value for the resistance to angular motion about that particular axis. We also have the parallel axis theorem and the perpendicular axis theorem, which helps us translate that resistance to a different axis once we know it about a certain axis. So the angular momentum principle, remember, we have this idea of linear or translational versus angular or rotational. We have basically the motion of a circle now of a certain radius. We have an initial position, an initial velocity, a final position, a final velocity. We have counterclockwise motion being positive, clockwise motion being negative. We have this idea of arc length, this angle here, representing a certain arc traveled. If we go all the way around, that becomes the circumference. We also have the idea of a cross product producing a third vector in a direction perpendicular to the first two, and that would apply to torque, angular momentum, angular acceleration, angular velocity, and so on. And we use our right hand, not our left hand. And the linear formulas and the angular formulas are very similar to each other. You just kind of swap out the variables, and we have our 5 kinematic equations just easily being able to be converted there. We have the idea of uniform versus non-uniform circular motion, one of which is only change in direction, and then we can add on an additional tangential acceleration or angular acceleration if we want to. And then we have the idea of centripetal force, where we need some sort of a force in order to hold us in that circular motion, which is supplied by real forces. And we have linear versus angular units as well, but it's fairly analogous. And we come to the idea of the angular momentum principle by just kind of converting over our formulas. And so we have F net equals ma goes over to torque net. And then we got momentum to angular momentum, translational kinetic energy to rotational kinetic energy, and then we can basically take our momentum principle, which was the first principle that we learned, and we can put it over into the angular momentum principle and easily convert that over just by swapping the variables. And now we have a new tool for dealing with angular motion versus just linear motion. So let's apply this to two different problems here. This first problem has to do with a merry-go-round, and we have the merry-go-round has a radius of 1.6 meters, and we have a mass of 200 kilograms, and so we actually have some numbers here. And so we have a kid as well, 50 kilograms, riding on the edge of the merry-go-round here, and at a particular point the kid will jump off, and when that kid jumps off, he'll move at a speed of v, 5 meters per second relative to the ground, and at an angle of 53 degrees below the x-axis here. And what we want to know is what is the initial angular momentum of the system, and that's for part 1. And what we want to know for part 2 is what is the final angular velocity of the merry-go-round. So we are going to use the angular momentum principle, and we will assume that there's no friction. We'll assume that the kid can be approximated as a point mass, and we'll assume that the speeds are much, much less than the speed of light. we will have the surroundings basically being everything else, and we're going to treat the merry-go-round as a disk and the kid as a point mass for our system. And in general, what we'll do is we can assume that there's no external torque, which means the rate of change of angular momentum is zero. There's no angular acceleration. What we can do is say that the initial angular momentum is equal to the final angular momentum, and so what we really just need to do is figure out what the total initial angular momentum is and what the total final angular momentum is, and then we can set them equal to each other. And so it's basically the idea of conservation of angular momentum. And so let's get into that here. What we'll do is, for part one, we'll figure out what the initial angular momentum is of the system here. And so we have the moment of inertia of the system here. We have to add the point mass to the disk, and so we have the kid plus the disk here moving at an initial angular velocity. And so the kid, we're just going to have as mr squared, so a point mass, and the disk we got 1/2 mr squared. And we have clockwise motion, which is negative, so we got that negative sign there. And we have a nice expression that we can get to once we kind of simplify it down a little bit, and we can plug in our numbers, and we actually get a value here for the initial angular momentum of our system. And then for part two, we will look at the net torque being zero, so there's no change in that angular momentum. And so we can use the idea of angular momentum conservation. The final amount of momentum is equal to the initial amount of momentum. And so we need an expression for the final amount of momentum for that system. And so in this case, the disk is going to be somewhat easy. We don't have the point mass anymore of the kid, so we can just use the 1/2 mr squared times the final velocity, whatever that may be. And the kid, though, we want to look at the perpendicular velocity here. So we have this mvr perpendicular, and what we'll do there is we need mvr sine theta. So sine of theta is that opposite. So we want to look at the amount of velocity which is perpendicular or tangential. And so we can substitute in our numbers here, and we get the negative 192 from part one that we can plug in here, and we get the 50 and the 5 and the angle that we plug in and everything, and we will eventually get to a final angular velocity of 0.497 radians per second. And so that is problem one. We'll look at problem two here. This one is a string wrapped around a uniform disk, and we have the mass given to us, the radius given to us. We also have these four masses attached as well as point particles, and a distance b away. And the moment of inertia of those point masses is mb squared and 1/2 mr squared for the disk. And so for part one, it's asking what is the angular speed of the apparatus, and for part two, what is the angle through which the apparatus turns in radians or degrees. So we're going to use the angular momentum principle. We're going to assume that there's no friction about the axis of rotation. We'll assume that all the speeds are much smaller than the speed of light. We will assume that that we're going to use the system of the disk and the masses, and the surroundings is basically just your hand. And we can basically describe this general strategy that we're going to use here. We're basically saying that the net torque is equal to the rate of change of angular momentum. So the final minus the initial angular momentum divided by time. And so that's basically the angular momentum principle. And so we'll find the left-hand side and the right-hand side, and we'll set the left equal to the right. And we can also note that the angular displacement is the average angular speed divided by time. And so we'll get into it here. So for part one, here's the angular momentum principle, and we are going to say that the net torque here is going to be a force acting at a certain radius away, so Fr, and that's also causing clockwise motion, which is negative, and so we got that negative sign, and we're going to set that equal to the change in angular momentum over time. And so we know that initially the system is at rest, and really all we need then is the final, which is the moment of inertia of the system times the final angular velocity. And the system inertia is going to be the masses plus the disk, and so we have to add that together in order to get the total system resistance to angular motion. And then we will plug in our numbers here, and we know that this happens over a time period of 0.2 seconds, and then we can substitute everything in, and we're good to go here. So we can solve for the final angular velocity to be negative 11.96 radians per second. Now for the part two here, we know that the angular distance is basically just the average angular speed times the time. And so we know that the average here is going to be final plus initial over 2. And so we have the final being 11.96, and the initial is 0 over 2. And so multiplied by that time, and we get your angular distance here of 1.196 radians. And so that's the two problems here illustrating this angular momentum principle a little bit more. The first one had to deal with that merry-go-round and the angular momentum, and this one dealing with a string which is pulling on this disk and rotating it, which also has to do with that angular momentum. And we will see you in the next one.